All right, welcome to lecture video part 1 of 2.2 equilibrium and yield. Let's look at the content of this video. We'll be focusing on the first 3 boxes. First one is the chemical systems may be open or closed. That's just an idea that you need to know. It's a definition thing. And next one, over time, reversible chemical reactions carried out in a closed system at fixed temperature eventually reach a state of chemical equilibrium. Next one, the changes in concentration of reactants and products as a chemical system reaches equilibrium can be represented graphically, and what we need to be able to do is to draw and interpret graphs representing changes in concentration of reactant and products. We'll skip this next slide because that's in probably the third part of the video. All right, now let's talk about chemical equilibrium. First thing that we need to talk about is that the reactions that we know, they are mostly reversible. Okay, forward and backward reactions actually occur almost all the time. The symbol two-way arrow is usually used, the one that looks like that, instead of just one-way arrow. Why? Because it's just simply replaceable. Reversible, that's the word. And they are the symbols that you should use. The one at the top shows the reaction is happening to two directions, both directions, and just one-way arrow just shows that it's one way, or it just prefer to be making products and it's hard to come back. For example, things being exploded, it's very hard to put it back to reactants, as well as things being digested or decomposed, very hard to reverse it back. But a lot of reactions are actually reversible. All right. When the reaction is at chemical equilibrium, both forward and back reactions are still occurring, but at equal rates. So the speed of going forward and speed of reaction going backwards equal to each other. That's what we call it as equilibrium. Nothing seems to be happening. It appears that no reactions occurring at all. Like everything is settled, but reactions are still happening. The reaction is, this reaction is said to be in dynamic equilibrium. There's no apparent change, but things are still happening at molecular atomic size. There's a video that we could watch. If you want to pause this video and click on the link from the link to this lecture note, you can do that once you watched it. Next bit. For reaction to reach equilibrium, the system must be closed. There we go, closed. So nothing is escaping. Nothing is being being able to be added to. Closed where reactants or product can be lost. So there's no loss, there's no gain of those products and reactants. It also needs to happen at a constant temperature. Now, what it's saying is that the temperature of the vessel cannot be changed externally. It can still contain a heat inside, it will come to the place where temperature increase or decrease wouldn't occur anymore. That would be where the equilibrium has been reached. All right. Dynamic equilibrium. A bit more notes on that. While a reaction in equilibrium shows no observable change, apparent change, no observable change, it is important to note that this equilibrium, it's not static. Still happening. Okay, there is constant motion between reactants and products. They are being formed and used up at the same time. Rather, the rate at which reactants and products forms is steady. Dynamic in here means that there's a constant interchange between reactants and products. This is similar to person going up and up the down escalator. You can see the diagram right below, above me. So yeah, like that. Whoops, like that. So the escalator is going down, but this person is trying to go up. There is no apparent change in the position for where he is. There is no apparent change, but things are happening. I'm gonna just keep myself being disappeared because I wanted to show that graph. A graph of concentration versus time can also be used to show the chemical equilibrium reaction. These graphs also show the ratio of product to reactant. When drawing these graphs, make sure the lines are lines are neat, and once equilibrium reached, use a ruler to draw the lines. Now, it says lines, but there's a specific type of line. You may have guessed it, but let me just grab a few different colors. So if you're drawing a graph, x-axis going time, there's a weird M there, time, and this being concentration, molar, time being, let's say, second, whatever's really fine. Okay, now if you had certain amount of reactant, you would start with that point and might end up around here. Start fast, and then the curve or the slope should go down because the rate of reaction should decrease. Oh, one thing I forgot to do not draw that because what you should be drawing is where the equilibrium has been reached. Let's say that the equilibrium has been reached at this time. Just saying EQU, not equation, it's equilibrium. Reaction rate starts to go down fast, and then at the equilibrium point, concentration should not change. So I've drawn the flat line. It should be parallel to the x-axis here. If you are drawing concentration of products formed as well, sometimes you get, on the slide that you see, it starts actually midway of the y-axis, so there was some certain concentration of product already existed. In my example, I might just start with 0. So same sort of rate, things appear and being formed, but at equilibrium, I try to draw it as a parallel to the x-axis. But yeah, they're all parallel here because there is no change in concentration anymore after equilibrium has been reached. And it is important that you draw this with a ruler and then make it neat and tidy, alright? Otherwise you might not get a mark. Moving on to the next one. Alright. Explanation of why equilibrium occur. Let's consider this reaction. 2HI gas that becomes, I should be using the right symbol there. H2 and I2. Two-way arrow is used, but different symbol there. What does occur? Well, at the beginning, as the hydrogen iodide, HI, is heated, it decomposes. The rate of decomposition, is initially high because HI, the concentration of HI is high. However, as the HI concentration decreases, the rate of forward reaction also decreases. This is because at the same time the backward reaction occurs and HI concentration is less. As H2 and I2 concentrations increase, the rate of back reaction will also increase. Eventually, I think that's the last line, or second last. Eventually, the rate of forward reaction will equal the back reaction. Therefore, before equilibrium has been reached, the rate of forward reaction is greater than that of the back reaction. Okay. Now, this is talking about rate of reaction versus time, which is different from what I was showing here. This one is concentration versus time. Okay. But the context of the HI example, it said rate of reaction versus time, they become the same for reactants and product being formed. If you look at next slide here, you can see what it looks like if you are tracking the rate of reaction forward and reverse and what happens at equilibrium. There's straight down equilibrium, dotted line that shows where the equilibrium occurred at a certain time. It says the rate of the forward and reverse reaction are now equal. Dynamic equilibrium has been achieved. Okay. At equilibrium, the rate of forward reaction equals the rate of the back reaction. And you can simulate that by using that chemarizona.edu. There's a flash that you can run. It was not available when I tried it last time, but we could try. Let's see if that's still available. Apparently the site has disappeared, so I'll see if I can find any alternative to it or not, but oh well. I will probably show what happens if you change things around. Let's also talk about this thing called observable equilibrium. During equilibrium, there are several macroscopic, which is something that you can see with your naked eyes, observable changes or properties of a system that will remain constant. Okay, at equilibrium, they are not. They are said to be constant. Those things are temperature of the system. If the reaction was producing heat, the heat will stop increasing or decreasing. It will remain constant. Pressure of the system, again, it's in a sealed container because that's what the closed system means. Nothing is escaping. So pressure in there should be stabilized. If it created gas as a part of reaction, there's nowhere that it can escape. Therefore, you'd be seeing the flattened down pattern for the pressure if you are measuring pressure. Color change, yeah, once it reaches the equilibrium, say if you're dealing with color change from, I don't know, purple to green, for example, there would be an end point to the change color until you open the closed system. pH is the same. If you are tracking a pH value change, it will settle down at some point. This should allow you to recognize that the system has reached its equilibrium. So again, no observable change is the way that you can observe that. There are two graphs that you can see. These are showing again concentration versus time. In the first graph, which is very similar to what I was drawing before on the board, A to B is what you're tracking, A becoming B. It seems like a lot of A gets consumed and a lot of B is being formed here. So B is the concentration of the product. As you can see, I'm gonna just point out here, if you're looking at this reaction as a two-way reaction, you can see that the arrow going to the arrow going forward is much larger than arrow going backwards. That's showing that the tendency of A becoming B is a lot more than B becoming an A, because it doesn't have to be 50-50. Okay, you don't always get the tendency of backwards and forward reaction to be the same. Tendency of A becoming B is a lot more due to, well, I guess what sort of stability A wants or B already has. Whereas if you reverse the reaction, if you focus on that, so B is where you're starting and A was 0 originally, and you just start the reaction, B becoming A. B is being consumed a bit, not much A is being produced here. So B to A is what you're looking at, but yeah, it's not much. B becoming A should be much less here, because A becoming B is always preferred in the same reaction. Either way though, it will reach to its dynamic equilibrium, okay, whenever the line hits the flat. Okay, so concentration doesn't change anymore at 60 onwards for reaction number 2, and for reaction number 1 at 80 seconds it has reached to its equilibrium, dynamic equilibrium. So that's something that you can get by interpreting graphs. All right. Something that I already mentioned before, if you are tracking rate of reactions over time, you'd be seeing that the rate of reaction going forward and going backwards would become the same when the system reaches to its equilibrium. Okay, and it becomes horizontal. Oops. Equilibrium system classes. There are a few different equilibrium that we can talk about. One is equilibrium system being heterogeneous, and the other one being homogeneous. Heterogeneous equilibrium mixture has reactants and products having different states. For example, BiOCl, what's that? Bismuth hypochlorite, which is solid. If it's dissolved into HCl solution, hydrochloric acid solution, it becomes bismuth chloride, which is solid, and then water. So it's heterogeneous because things that's involved have got solid, aqueous, solid, liquid, 3 different states. Whereas homogeneous equilibrium mixture, that's something that we'll deal with more so. Reactants and the products are in the same state. For example, here CO2 plus H2 gas, that becomes CH3OH, which is methanol. Don't worry about Kc expression, the word Kc expression just above here yet, because we'll cover that in the next video, which is this one. So just know that the definitions of things, I might just go back to first slide, not the first, second slide, to talk about first 3 boxes. If things can escape, the system for the chemical reaction is said to be opened. Whereas if nothing can be lost, whether it's a products or reactants, you call that as closed system. Over time, reversible chemical reactions carry out in a system, closed system at fixed temperature eventually reach a state called chemical equilibrium, specifically dynamic equilibrium. The change in concentrations of reactants and products as a system reaches to equilibrium can be represented graphically. There are a few ways of doing it. If you're tracking concentration versus time, or reaction rate versus time, or grams of loss or gain over time, you can do that. you need to also be able to interpret graph. Something that I introduced was which way of the same reaction, like forward or backward reaction, which one is more preferred, or is it hard reaction to occur or not. Alright, that's about it for this video. I will see you in the next video where we'll talk about KC expression.